Look at Mars today. It is a world of absolute unyielding desolation. A frozen, rusted desert where global dust storms can rise up and swallow the entire planet, hiding surface features the size of continents from our telescopes for months at a time. These storms are not merely visual events. They are towering walls of abrasive grit that scour the landscape, charging the atmosphere with static electricity and darkening the sun for weeks on end. The silence here is deafening, broken only by the hiss of thin winds and the occasional crack of rocks cooling in the twilight. The average temperature hovers around -80 degrees Fahrenheit, colder than the deepest interior of Antarctica. It is a cold that seeps into the bedrock, locking the planet in a permanent cryo-freeze. At the poles, the air itself freezes, with carbon dioxide turning into dry ice snow that blankets the dunes in a surreal winterscape. The atmosphere is vanishingly thin, 100 times thinner than Earth's, and composed almost entirely of suffocating carbon dioxide. To stand on these plains without a pressurized suit wouldn't just mean suffocation. The atmospheric pressure is so low that the moisture on your tongue, in your lungs, and in your eyes would boil instantly at body temperature. This phenomenon, known as the Armstrong limit, makes the very act of exposure a lethal event within seconds. It is a radiation-bathed wasteland where UV light sterilizes the surface daily, and the soil itself is toxic, laced with perchlorates that would destroy the thyroid gland of any human colonist. It appears, by all accounts, to be a planet where hope goes to die. A geologic corpse drifting in the black void of the inner solar system. But rewind the cosmic clock. Go back 3.5, maybe 4 billion years to a mysterious time period planetary scientists call the Noachian era. The picture changes dramatically. It shifts from a monochrome red to a vibrant, dynamic palette of blues, whites, and grays. Imagine standing on the edge of the Valles Marineris Canyon, looking out not at a sea of dust, but at a shimmering sea of liquid water. You would see white-capped waves crashing against a rocky shoreline, driven by thick, humid winds. You would feel rain, actual droplets of fresh water, falling from a heavy, protective atmosphere that shielded the surface from deadly space radiation. Beneath blue skies, towering cumulus clouds drifted over a world not too different from our own primordial Earth. Flash floods carved through the uplands, and gentle streams meandered through lush valleys, sculpting the terrain in real time. It was a world that could have supported rivers, lakes, and perhaps even biology. In the distance, the great Tharsis volcanoes might have risen as island chains, spewing steam and ash into a wet sky, replenishing the atmosphere with vital gases. For over a century, since the days of astronomers peering through brass telescopes at blurry markings they mistook for canals built by a desperate, dying civilization, dreamers have asked the same haunting question: did Mars once have oceans? Today, we aren't just speculating anymore. We are investigating. The rovers driving on the surface, the orbiters scanning with ground-penetrating radar from above, and the data streaming back to Earth across millions of miles are screaming the answer. The red planet was likely once a blue marble. In this episode, we are going to dive deep into the forensic evidence of ancient Martian water. We will virtually walk through dry riverbeds that dwarf the Amazon, analyze the chemical fingerprints locked inside the rocks, and reconstruct the colossal ocean that may have covered a third of the planet. We will piece together the puzzle of a planetary climate change so drastic it makes anything on Earth look trivial. And finally, we will confront the most difficult question of all. If Mars was once a warm, wet water world, Where did it all go? This is the story of the lost oceans of Mars. The first clues weren't found by microscopes or chemical labs, but by simple geography. When the Viking orbiters arrived in the 1970s, they circled the planet and beamed back grainy black and white images that confused geologists back on Earth. They expected a cratered wasteland like the Moon, preserved in vacuum for eternity. Instead, they saw scars on the planet's face that shouldn't have been there. These weren't just the circular impact craters left by asteroids. These were winding, meandering channels, some hundreds of miles long and miles wide, that branched out like veins in a human body. These features fall into two distinct categories: the branching valley networks that look like rain-fed river systems, intricately carved into the highlands, and the massive outflow channels that look like the aftermath of catastrophic groundwater bursts. Consider Ma'adim Vallis, a channel larger than the Grand Canyon. It cuts through the Martian highlands and empties into Jezero Crater. Or look at Jezero Crater, where we see a preserved fossilized river delta so complex it looks like the Mississippi seen from the ISS. These structures look suspiciously, undeniably, like the dried-up river systems of the American West or the Amazon basin. The geometry of the curves and the slope of the banks perfectly match the hydrodynamic equations used to model rivers on Earth. Take a closer look at Jezero Crater, the landing site of NASA's Perseverance rover. From orbit, the topography tells a clear, undeniable story. We see a winding channel cutting through the crater rim, opening up into a massive fan-shaped deposit. In geology, there is only one known way to create this specific structure. It's called a delta. On Earth, deltas like the Mississippi or the Nile form when a fast-moving river carrying tons of sediment hits a standing body of water, like a lake or an ocean. The physics are precise. The water slows down instantly, losing the kinetic energy required to carry its load, and the dirt drops to the bottom, building up layer upon layer of mud over thousands of years. We can even see the specific top set and bottom set beds in the orbital images, distinct layers that mark the changing water levels over centuries. These layers are essentially pages in a history book, recording the rise and fall of the lake's shoreline over millennia. To understand the sheer scale of what we are looking at, we have to look at the energy involved. Scientists estimate that to carve the valleys we see today, water had to flow not just for weeks, but for at least 100,000 years. Some of the larger outflow channels show evidence of flow rates 1,000 times greater than the Mississippi River at flood stage. We are talking about cataclysmic volumes of water, moving with enough kinetic force to drag house-sized boulders across the landscape, scouring the bedrock down to its very core. This was a planet defined by the raw, kinetic power of moving fluid. The physics of fluids is universal. It works the same on Mars as it does on Earth. You cannot form a structure like the Jezero Delta with wind. Wind scatters sand chaotically. It doesn't pile it into organized, layered fans. You can't form it with lava flows, which cool and solidify in entirely different patterns. You need water, and not just a brief trickle from a melting glacier. You need liquid, flowing, persistent water acting over geologic timescales, centuries, millennia, perhaps millions of years. But the most compelling physical evidence might be much smaller, something you could hold in the palm of your hand. Let's look at what the Curiosity rover found in Jezero Crater, thousands of miles away. It found pebbles. These weren't jagged, sharp fragments blasted apart by meteor impacts. They were rounded, smooth, and polished. Think about the stones you find in a riverbed or on a beach. Why are they round? Because they've been tumbling in a current, banging against other rocks, smoothing out their rough edges over miles of travel. This process, called abrasion, takes time and sustained energy. A single flash flood wouldn't do this. It requires a consistent, grinding force applied over seasons or years. Curiosity found sedimentary rock made of these rounded pebbles cemented together, a rock type called conglomerate. By measuring the size of these pebbles, hydrologists used the laws of physics to calculate the force of the river that moved them. This wasn't a seasonal trickle. This was a vigorous stream, ankle deep to hip deep, flowing at about 3 feet per second. This tells us that Mars didn't just have water events. It had a water cycle: evaporation, condensation, precipitation, and flow. Rivers flowed, lakes filled, rain fell, and the cycle repeated for eons. The planet was alive with the sound of moving water, but rocks can be deceptive. Wind and erosion can mimic the look of water erosion if given enough time. To be absolutely certain, we need to look closer. We need to analyze the chemistry of the ground itself. We need to interrogate the atoms using spectroscopy. When the Opportunity rover bounced to a landing in Meridiani Planum in 2004, it woke up in a strange, alien landscape. It found tiny, spherical spheres scattered across the bedrock, like marbles spilled from a bag. The mission team famously called them blueberries. These aren't biological fruits. They are concretions of a mineral called hematite. On Earth, hematite concretions form in a very specific way. Groundwater saturated with dissolved iron flows through porous rock. As the chemistry changes, the iron precipitates out, growing these hard little spheres layer by layer inside the rock before erosion reveals them. Finding these blueberries was the first direct proof that groundwater once soaked the Martian crust like a wet sponge. But the story gets more complex. Orbiters like the Mars Reconnaissance Orbiter have mapped the planet's mineral timeline. We see a distinct shift. The oldest rocks, from the Noachian period, are rich in phyllosilicates, or clays. You cannot bake a cake without flour, and you cannot make clay without water. Specifically, you need water interacting with volcanic rock in a neutral, non-acidic environment for very long periods. This clay era suggests a time when Mars was wet and temperate, friendly to life. It points to a pH balance that was not harsh or corrosive, but potentially drinkable and inviting to cellular biology. But above the clays, we find something else: sulfates, salts. As Mars moved into the Hesperian era, the climate changed. The water became acidic and salty. As these ancient lakes evaporated, they left behind thick crusts of sulfur and salt, much like the salt flats of Utah or the Dead Sea on Earth. This chemical layer cake tells us the story of a dying planet. First lush and wet, then drying and salty, and finally, frozen and dead. This transition marks the exact moment the planetary systems began to fail. But here is the smoking gun. It's in the atmosphere itself. Water is made of hydrogen and oxygen, H2O, but there is a heavier isotope of hydrogen called deuterium. This heavy water is twice as massive as normal hydrogen, making it much harder for the sun to strip it away into space. When scientists analyze the current Martian atmosphere using powerful spectrometers, they find a ratio of deuterium to hydrogen that is 8 times higher than on Earth. This is a mathematical footprint. It implies that Mars has lost a massive amount of its lighter water to space, leaving the heavy stuff behind like the salty residue in a boiling pot. Calculations based on this specific ratio suggest that Mars once had enough water to cover the entire planet in a global ocean about 137 meters, 450 feet, deep. But since Mars isn't flat, gravity would have pulled that water into the lowest points, forming a real, deep, hemispheric ocean. If you look at a global topographic map of Mars, you notice something strange immediately. It's a feature called the hemispheric dichotomy. The southern hemisphere is high, rugged, ancient, and heavily cratered. The northern hemisphere, however, is incredibly flat, smooth, and sits miles lower in elevation. It looks as if someone took a giant knife and sliced the top third of the planet smooth. It is a perfect basin. In fact, it is one of the largest basins in the solar system. This is where many planetary scientists believe the ancient ocean lay. They call it Oceanus Borealis, the Northern Ocean. The smoothness of these northern plains is likely due to billions of tons of sediment settling on the ocean floor, burying the ancient craters underneath. Imagine an ocean the size of the Atlantic, covering 1/3 of the planet's surface area. It would have held more water than Earth's Arctic Ocean. Standing on the shore near what is now the Cydonia region, you wouldn't see the other side. You would just see the curvature of the horizon, perhaps broken by the peaks of ancient volcanoes rising as islands. This basin is so vast and so flat that if you were to stand in the middle of it, the planet's curvature would be the only topographic feature visible. But is there proof for a shoreline? Coastlines are fragile things. They degrade over billions of years of wind erosion, making them hard to spot. Scientists have traced potential contacts, known as the Arabia level and the Deuterium level, which look suspiciously like constant elevation beaches. But without walking there, it's hard to be sure. However, there is evidence of violence that helps us map the water. In 2016, researchers studying the northern plains found evidence of mega-tsunamis. They believe two massive meteor impacts, one of which likely created the Lomonosov crater, hit this northern ocean roughly 3.4 billion years ago. These weren't just splashes. The impact would have generated waves up to 120 meters, 400 feet high, taller than a 40-story skyscraper. These waves rushed inland at the speed of a jetliner, tearing up the landscape and depositing boulders, mud, and ice hundreds of miles from the shore. The sheer momentum of these walls of water would have scoured the bedrock clean, reshaping entire regions in a matter of hours. We see these thumbprint terrain patterns in the Arabia Terra region that strongly resemble tsunami deposits found on Earth after the dinosaur-killing asteroid hit. The logic is simple. You cannot have a tsunami without a massive body of water for the energy to travel through. So we have the basin, we have the chemical signal, we have the ancient shorelines and the scars of tsunamis. The picture seems clear. Mars was wet, it was a blue world. But this leads us to the tragedy of Mars. How does a world lose an entire ocean? If Mars was a blue paradise, what happened? How did a world with a thick atmosphere and deep oceans turn into a freeze-dried husk? The culprit is the heart of the planet, or rather, the death of its heart. On Earth, we are protected by a magnetic field, a global, invisible shield generated by our churning, molten metal core. This geodynamo acts like a force field, deflecting the solar wind, a relentless stream of high-energy protons and electrons shooting out from the sun at 1,000,000 miles an hour. Without it, our atmosphere would be stripped away. Mars once had this shield too. We find magnetic footprints in the ancient southern rocks. But Mars is only half the size of Earth. It lost its internal heat much faster. About 4 billion years ago, the Martian geodynamo, the magnetic heart, slowed down and stopped beating. The lights went out. Without the magnetic shield, the sun became a killer. The solar wind began to batter the upper atmosphere, stripping away the air molecule by molecule. This is a process called sputtering. NASA's MAVEN mission has been orbiting Mars, watching this happen in real time. It confirmed that even today, Mars is losing gas to space at a rate of pounds per second. In the past, under a younger, more active sun, this loss would have been catastrophic. It wasn't a sudden death, but a long, slow suffocation. It was an atmospheric erosion that peeled back the layers of the sky until there was nothing left to hold the heat. Without a thick atmosphere to provide pressure, liquid water cannot exist on the surface. It's simple physics. As the pressure dropped, the boiling point of water dropped with it. The ocean boiled away into gas or froze into ice. Even worse, ultraviolet light split the water vapor molecules apart. The hydrogen, being light, escaped into space, never to return. The oxygen reacted with the iron in the ground, literally rusting the planet red. Mars bled its ocean into the void and rusted its surface in the process. But not all of it left. Recent radar data from the Mars Express orbiter suggests that a significant amount of water didn't escape up. It went down. Massive deposits of water ice are buried under the poles and beneath the dust in the mid-latitudes, enough to coat the planet in a shallow sea if melted. Even more intriguingly, radar reflections from beneath the South Pole suggest pockets of liquid water, super salty brines, might still exist deep underground, kept liquid by the pressure and the planet's remaining internal heat. The ocean didn't just vanish. It went into hiding. It retreated into the dark, insulated crust, waiting for a thaw that may never come. Here is the multi-billion-dollar question. The reason we spend vast fortunes sending delicate robots to a rusty rock millions of miles away. On Earth, the rule is simple. Everywhere we find water, we find life. From the deepest, darkest pressure cooker trenches of the Pacific to the boiling acid springs of Yellowstone, and even inside the nuclear reactors of Chernobyl. Life finds a way. If Mars had oceans for hundreds of millions of years, did life have enough time to start there too? We aren't talking about civilizations, cities, or little green men. We are talking about microbes, single-celled organisms that might have thrived in those ancient deltas, feeding on the chemical energy of the rocks or the sunlight filtering through the water. Right now, the Perseverance rover is collecting samples from that river delta in Jezero Crater. It is focusing on the Martian unit, a ring of carbonate rocks that could have formed at the edge of the ancient lake, the prime real estate for ancient beach-loving microbes. It is drilling chalk-sized cores of rock and sealing them in sterile titanium tubes. Each tube is hermetically sealed to preserve the volatile compounds inside, ensuring that no Earth bacteria contaminate the pristine Martian record. It is hunting for biosignatures, molecular patterns, isotopic ratios, or fossilized mats called stromatolites that could only be created by biology. But we must also consider the potential that life didn't just stay in the water. We have found organic molecules, the very building blocks of biology, preserved in Martian mudstones. Curiosity has detected spikes of methane, a gas often produced by living things, puffing out from the subsurface. While not proof of life, these are tantalizing hints that the chemistry of Mars was, and perhaps still is, active. If life ever took hold, it might have retreated deep underground as the surface died, following the water down into the dark, warm aquifers below. If Mars was wet, it was habitable. That is a scientific fact. But habitable doesn't mean inhabited. A house can be perfect, but that doesn't mean someone lives there. However, consider this. Life appeared on Earth roughly 3.8 billion years ago, almost as soon as the planet cooled down enough for water to exist. This timing coincides perfectly with the wet period on Mars. If life is a natural, inevitable consequence of chemistry and physics, then a wet Mars should have been alive. This leads to the fascinating theory of panspermia. We know that rocks from Mars travel to Earth as meteorites. If Mars cooled down and had oceans before Earth did, is it possible that life started there first and hitched a ride to our planet on a rock? In a strange twist of fate, are we the Martians we have been looking for? The biological potential of this ancient ocean opens up a universe of possibilities that makes the silence of the current desert even more profound. Finding a fossil on Mars would change everything. It would mean we are not a miracle. It would mean the universe is teeming with life, waiting to be found. It would shift our philosophy, our religion, and our understanding of our place in the cosmos. It would prove that the spark of life is not unique to Earth. The story of water on Mars is a story of a planet that died too young. It's a cautionary tale of planetary evolution, a reminder of how fragile a biosphere really is. It reminds us that Earth is an anomaly, a precious oasis protected by a magnetic shield that we must not take for granted. Mars shows us what happens when a planet's heart stops beating. We now know, with near certainty, that the red dust we see today was once wet mud. The dry, silent canyons were once filled with the roar of rushing rivers, and the empty northern plains were once a vast, reflecting ocean under a younger sun. Mars was Earth's twin, a blue marble that turned red. In the coming decade, a daring mission called Mars Sample Return aims to launch a rocket from the surface of Mars to bring those tubes collected by Perseverance back to Earth. It is one of the most complex engineering challenges ever attempted, catching a canister of rocks in orbit around another planet and transporting it safely across the void. But when we get those rocks into our best laboratories, when we can put them under electron microscopes and subject them to synchrotron radiation, we might finally confirm what we've suspected for years. Did Mars have oceans? Yes. Did Mars have life? That answer is waiting for us in the red dirt, waiting to be dug up. What do you think? If we confirm that Mars had life, does that make you feel less lonely in the universe, or more terrified of the great filter that wipes civilizations out? Let us know your theories in the comments below. If you enjoyed this deep dive into the lost history of the red planet, please hit that like button and subscribe. We are building a community of space explorers here, and we want you on board. Until next time, keep looking up